One way to analyze the processing of an audio effect is to compare the amplitude of our output signal versus the amplitude of our input signal. This is a little bit different than when we were plotting the waveform, which is amplitude versus time. In this case, what we like to do is figure out if our input signal has an amplitude of 0, what is the amplitude of our output signal? If our input signal has an amplitude of 0.5, what is the amplitude of our output signal? And we like to do this systematically over the entire full scale range from -1 to 1. This type of analysis works great for a certain category of audio effects, and that's when our output signal at the current time sample is a function only of the input signal at the current time sample. So let's go through and look at a comparison of our output to our input amplitude by using some linear processing. First, we'll look at multiplication, which is going to change the signal's gain, and then we'll use addition to perform DC offset. Let's begin with a basic example here in MATLAB. I've already started this script that we can use to demonstrate this type of visualization for audio effects. I created an array, which is the few values that I assigned to the variable x. I'll run the script. If I want down here in the command window, can print out what elements are stored in the array x. Also, I can do operations on this array. So I can do 3 multiplied by x and look at the result. As we would expect, each element in x has now been multiplied by 3. So -1 becomes -3, -0.5 becomes -1.5, and so on. We could also visualize this by using the plot command. Here, I'm going to put in 2 input variables or arguments. First, I'm going to put in the variable x. That's what we'll use along our horizontal axis. And then, for our second argument, I'm going to put in 3 multiplied by x. It's going to be our value that's used along the vertical axis. Run this script. We see that we end up with this straight line. I can follow along the different values. So for our horizontal axis here, have the variable x. We're going to have a value of -1 to begin with. When that's true, what we have here for our second argument, 3 multiplied by x, for the vertical axis, have a value of -3. Go to our next value here of -0.5. You multiply that by 3, we end up with this -1.5. So this is actually the way that we can visualize a way of processing the signal. So in this is equivalent to a gain change here. So instead of using the variable x, I could have something like input. And we could then have the output is equal to 3 multiplied by our input. And then change these variables in our plot function. So now we're going to compare our input to our output. Just like we saw before, we're looking at our input when it's on a scale, anything in between -1 up to 1, we can look at what our output signal is going to be. Just for comparison's sake, let's look at in here if we're going to put in some more input arguments. We'll plot 2 lines now. Plot our input compared to 1 multiplied by our input, and then we'll plot our input compared to our output, which is 3 multiplied by our input. This is a nice way to do it because we can look at what would happen if there was no processing. Our blue line here indicates our result for what would happen if we just had our input multiplied by 1. So no processing at all. You'd see that when our input has a value of -1, what we'd have along our vertical axis is also -1. That line will continue 0 and 0 and all the way up here to 1 and 1. But then when we multiply by 3 and we get our output signal, we can see how the slope changes. So actually a way to think about a gain change is that we're going to be changing this slope of the line, the relationship between input and output. Similarly, if we were to go in here and make some other change like 0.5, so instead of increasing the amplitude, we're now decreasing the amplitude. You can look at the result. And now what happens is our blue line is our one-to-one relationship where your input just becomes your output, no processing at all. We multiply by 0.5, the processed signal here, way of visualizing it in red, we see that when we had a value of -1 for our input here, our output is now going to have a value of -0.5. As we increase the value from -1 up to 1, we can see how our output signal is going to change, right? We've now changed the slope of this line. Before, when we increased the slope, that was an increase in our gain. When we decreased the slope now, it's going to be a decrease of gain. Let's also look at, instead of multiplying here to perform the gain change, let's look at what would happen if we were to perform addition for a DC offset. How about 0.5 plus 0.5? So in this case, what it's going to do, blue is our original signal again, where there's no processing. When we perform DC offset, it shifts everything up by that amount. So when we had an input of -1, we add 0.5 to it, and now the output has a value of -0.5. We have the slope that's the same because we're not changing the gain. It goes all the way up here to when our input has a value of 1, our output is going to have a value of 1.5. Hopefully that all makes sense. We could combine these two things together, have something like 2 multiplied by our input, and have a plus here. So not only are we going to change the gain, but we're also going to have some DC offset. We could have the Y-intercept then. So when our input has a value of 0, we can see that our output has a value of 0.5. Change the slope, and then also this Y-intercept or the DC offset. If this was inverting gain, if we had a negative here, we could see that the slope now becomes the reverse. So our red line, when our input has a -1 value, our output is going to have a positive value. When our input has a value of 1, our output has a negative value. That's what happens when you have this kind of inversion that occurs. So let's go back and change our input signal then. Rather than just having a few values, it seems to make sense and make it intuitive to follow along with. Let's create another kind of signal that might be more useful. Let's create an array that starts at a value of -1 and goes up by a step size of 0.01 and then finishes at a value of 1. I'm going to put in here that we're going to perform the transpose operator. So we're always working with column vectors here for audio. Let's go back and just set this to be, how about 0.75 and no DC offset. So this way, what we're able to do is plot more points rather than just a few sections along the way. -1, 0.5. We're plotting many different points along this full scale range from -1 to 1. So this is a common kind of signal that you can use to analyze a way of processing the signal. It has many different points that you measure, and you could just increase the resolution by adding in zeros here to the step size. But that should be sufficient. Believe it or not, you don't just have to use this signal that goes from -1 up to +1. We could also use a sine wave. So let's look at how this might work. So here we're going to want to use our input signal as a sine wave. We've been using this formula 2 times pi times f times t. We haven't defined f and t, so we might as well do that. Say f is 2 cycles per second. We could actually make it however many cycles per second we want, whatever frequency, as long as it's within our sampling rate. So let's define that too, 48,000. And let's go ahead then and create t. How about a 1 second long signal? So we'll go up step size of 1 divided by our sampling rate to 1. Let's transpose it. So before we start plotting it using this one, let me comment it out. Let's look at plotting the waveforms here. So if I plot t compared to our input signal and t compared to our output signal. I'm going to compare the waveforms here of input to output. Run this script and look at the result. So here what we're looking at is the amplitude over time. So we've got a 1 second long signal, but we can have some intuition then about, okay, when our blue signal here, our input signal, has a value of 0, our output signal also has a value of 0. As we go up, when our input signal has a value of 1, our output signal has a value of 0.5. We're scaling the gain on it here. That continues. When we reach down here of -1, we have a value of negative 0.75. So now if I switch back, look at our other way to visualize this, comparing the input and output amplitudes, then you can look at the result. Again, we're looking at straight lines here. Our blue one is just an unprocessed signal, and our red one is the processed, scaling the gain by 0.75. What do we see? When our input signal has a value of 0, our output signal also has a value of 0. That's what we saw before. When our input signal has a value of 1, we've now gone up and have a value of 0.75. So it's just a different way of visualizing the same kind of information. Rather than looking at it over the waveform, we're just looking at output amplitude versus input amplitude. This is a very important way to visualize the processing that occurs in different types of audio effects.